Okay, good morning, class. Let's move on to our second lecture under this module 4. In the last class, I have given you an introduction to how we can draw conclusions or inferences by using probabilistic approach. That leads us to get introduced to Bayesian learning. So we got this introduction to Bayesian learning and what is Bayes' theorem, and we understood what is prior probability, posterior probability, all these terms with respect to an example of a patient being diagnosed with cancer, being diagnosed as positive, and really assessing whether he has cancer or not. Right? For that, we have taken probability of a patient being diagnosed as positive when he has cancer and the probability of him being diagnosed as positive when he doesn't have cancer. This symbol is for not. Okay. So what is the probability of that patient being diagnosed as positive when he has cancer and when he doesn't have cancer? Those two probabilities we have calculated. These are called as posterior probabilities. Why? Because we are trying to find out whether this being diagnosed as positive holds good when he really had cancer and when he doesn't have cancer. Okay, that is called as posterior probability. Probability of H given D. Okay, so what the probability of this hypothesis holding good for the given training examples. When the training examples are given, whether this hypothesis holds good or not, that is called as posterior probability. For that, we have calculated the probability of that patient being diagnosed as positive when he has cancer and when he doesn't have cancer. In both of those probabilities, we calculated as that patient being diagnosed as positive when he doesn't have cancer, that probability we calculated as more. That is how we inferred that the patient doesn't have cancer though he is diagnosed as positive. Why? Because there is 3% chance or 2% chance according to the data they provided that this percentage of the time the test may be wrong, because diagnostic test may not be the complete measure to say whether a patient has cancer or not. In that cases, we try to conquer this probability, prior probability, and this percentage of error that may occur in the diagnosis. Okay, all these we have used, all this data we have used in order to say whether a patient really has cancer or not, whether when he is diagnosed as positive. Okay, refer to the previous video. This calculation is very important. In exam also you may get a problem on this to solve. Okay, in today's class, let's see Bayes' theorem and how it is related to concept learning. Now, what is the relationship between Bayes' theorem and the problem of concept learning? What is concept learning? In the first chapter itself, we have gone through this topic, concept learning. Concept learning is you're making the machine learn some concept by providing it some training data so that it can generalize well on unseen data. So when the training examples are provided, going through the training examples, it understands the behavior of the data, which attribute is playing an important role in predicting the outcome variable, which attribute is having less role in predicting the outcome variable. Say there are attributes A1, A2, A3, and the predicted variable Y. That is the outcome label. Now, this attribute may have larger importance and this attribute may have smaller importance. Let me add some drama to the technology here so that you'll understand better this concept. Say you're sleeping at night and when there is earthquake, you just experience some tremors in the earth or in the building that and you identified that earthquake is occurring. Now you have 5 minutes to decide what to save. Say your options are your loved ones. You want to save your loved ones, your certificates, and money, and your clothes. Say these are the things you wanted to save before getting out of the building in 5 minutes. So, what would be your priority? Obviously, your priority will be to save your loved ones, right? Then, if time permits, you may save the other things. So, what priority you are giving to these options are important. That is called as the weight that you assign to an attribute. You are giving more weightage to this option to save. Later, you may give weightage to this option, then this option, then this option. It means in deciding what you want to save in at the time of disaster, what priority you give for whom you want to save, that is called as the weight you assign to that particular attribute. In this case, a1, a2, a3, say a1 is playing major role in predicting y, you give higher weight to it. And if you have a2 is playing a moderate role in predicting y, you give some smaller weight to it, and A3 is not playing any significant role in predicting Y. In that case, you may eliminate that entirely from the learning task, or you may give it a very less weight. Okay, in that way, you have to make the machine learn the concept. Once the machine learns the concept, then when new data is given to the machine, it will be able to generalize and predict about that particular new data point. Okay, this is called as concept learning. Based on the training data you give to the machine, based on the training experience you provide to the machine, better will be its generalization capacity with the new or unseen data. Okay, that is called as concept learning. Now, how this Bayes theorem is related to concept learning, let's see. Posterior probability can be used as the basis for a straightforward learning algorithm that calculates the probability for each possible hypothesis, then outputs the most probable one. So what is posterior probability here? It is the basis for a straightforward learning algorithm that calculates the probability of each possible hypothesis. There may be many hypotheses, and all hypotheses may be fitting to your training examples. But which is the best one? You have many solutions. Which is the best solution? Which has the maximum likelihood to be consistent with the training examples given? Which has the maximum chance of being a better fit to the training examples given? That will be your most probable hypothesis. For gaining that, for calculating that probability, for knowing that likelihood of that hypothesis to be consistent with the training examples, we attach this probability concept to concept learning. And that is made easy by using Bayes theorem. Bayes theorem will help us to calculate the posterior probability of a hypothesis for the given training examples so that we can select the most probable hypothesis or the best possible solution. Now, before going in depth into this concept, let us see the basic probability formulas. These all you have learned in your school days. So it will be easy for you to just recollect. I'll start explaining. Immediately you can recollect. It is not, and there is nothing much complex in this. So what is the product rule in probability? Probability of A and B together, of a conjunction of two events A and B occurring together. What is the probability? You can represent it as probability of A given the details about occurrence of B multiplied by prior probability of B. Or you can also write it as probability of B given some details about the prior probability of A, that A has occurred before, multiplied by prior probability of A. Sorry, I have said prior probability here. Just cancel that. Probability of B given A means some knowledge you have about A's occurrence. Then can your knowledge about B's occurrence be refined? Can you get a better knowledge about B? Say if you want to calculate probability of B, you get some term. Now, can this estimation be improved if at all you are given the knowledge about probability of A occurred already? That is called probability of B given A. A has occurred, and if details are provided about that, then your estimation of probability of B, your calculation about probability of B can be refined. That is called as probability of B given A. Okay, multiplied by prior probability of A. Right? So this product rule, probability of A and B, can be expressed like this. Now what is the sum rule? Probability of a disjunction. Conjunction is represented by this symbol and disjunction is represented by this symbol or, and here we have plus for adding those two probabilities. Probability of A or B. Probability of A, either A occurs or B occurs. How do you calculate that? Probability of A plus probability of B minus probability of A and B occurring together. Subtract that. That will give you probability of A or B. How easy it is? It is probability of A occurring plus probability of B occurring. From that you subtract both of them occurring together, so that you will get the probability of either of them occur. Either A occurs or B occurs. That is probability of A or B. Did you understand? Now Bayes theorem. The posterior probability P of H given D means probability of hypothesis H holding good for the given set of training examples D. Of H given D, how do you write that? Probability of D given H multiplied by prior probability of H divided by prior probability of D. You know this theorem very well, right? That is Bayes theorem. Now theorem of total probability. If events A1, A2 and so on up to AN are mutually exclusive. What is mutually exclusive? If occurrence of one event excludes the occurrence of other event, then they are called as mutually exclusive events. Say when I toss a coin, head appears on the top. It excludes the chance of tail appearing on the top. When I toss a coin again, I get tail. I get tail on the top means event of getting tail on the top occurred, and it excludes the chance of head appearing on the top. Tail appearing on the top excludes the chance of head appearing on the top. Do you see any coin landing intermediary? Like say this is your coin. Either this happens or this happens. Coin doesn't stand like this, right? So that is called as that is called as mutually exclusive. Either head appears on the top, excluding the chance of tail appearing on the top, or tail appears on the top, excluding the chance of head appearing on the top. Those are called as mutually exclusive events. Is it very clear now? Now, if events A1, A2 and so on up to AN are mutually exclusive, means if one occurs, the other set doesn't occur. That is called mutually exclusive. With sigma I equal to 1 to n, add up all their probabilities and that should sum up to 1. Correct, right? If they are mutually exclusive, then all of them share equal probability. adding up to 1, because all of them are possible. Either head can happen or tail can happen. They have equal chances. In that case, their probability is 0.5 and 0.5, adding up to 1. So they are sharing equal probability because you have two events here. They share equal probability 0.5 and 0.5. If you have three events here, then they share an equal probability of 0.33, 0.33 and 0.33, summing up to 1. Right? That is called as theorem of total probability. How that can be expressed? Probability of B equal to add up probability of B given AI, an event in the probability set has occurred, multiplied by the prior probability of AI. That is called as theorem of total probability. So when I say that there is no prior probability details available about a hypothesis, then you have to immediately understand that we can assign equal probability to all the hypotheses in the hypothesis space. Say a hypothesis has 5 hypotheses. Hypothesis space has 5 hypotheses. Now you don't know prior probability of them. Means you doesn't know that one occurs better than the other. One has chances of occurring better than the other. No, you don't have any idea. In that case, all those 5 will share the probability 1. That is 1 divided by 5. Okay. What are the number of hypotheses in hypothesis space? I said 5. So 1 by number of hypotheses in the hypothesis space. All those hypotheses will share this probability 1. This is called as theorem of total probability. Is it very clear, students? Should I repeat any of these concepts again? At least one answer, yes or no? Speak out, students.
Ma'am, can you explain this theorem of total probability once again?
Yes, I'm glad to do that. Theorem of total probability is, say you have set of events and all of them are mutually exclusive events, right? Means if one happens, all other doesn't happen. Again, in the next turn, in your next experiment, if one of the events happen, others doesn't happen. Say you have set of events A1, A2, and so on up to an. Now, if A1 occurs, it eliminates the chance of others occurring. If A2 occurs, it eliminates the chance of others occurring. Means they are called as mutually exclusive events. If one event occurs, other events chances are excluded from happening. Okay. Now, in this case, if one event is occurring, its probability is 1. All other probabilities will be 0. Now, if another event occurring, its probability is 1. Other events can't occur now. Those then that case all will be 0. But you doesn't know which event will occur until you perform the experiment. In that case, we say that you don't have any knowledge about the prior probability. You don't have any knowledge about which event will occur out of these n events. A1, A2, A3 and so on up to AN, you have n events, but you doesn't know which event would occur. But you know that if one event occurs, other events doesn't occur. In that case, what do? You have to share the probability of 1 among all these n events. So each event's probability will become 1 by n. This is called as theorem of total probability. You are sharing the probability 1 among all the n events because you doesn't know which event would occur. All of them have equal probability, and that equal probability is denoted by 1 by n. Now, how it is represented here in terms of this mathematical formula? Probability of an event B can be represented as, again using Bayes' theorem, probability of B given any event that happened multiplied by probability of AI, probability of that event happened. Okay, that is nothing but P of B, because this and this will cancel. If that occurred, the other events doesn't occur. So it is same as probability of B. Did you understand, Umehani?
Yes, ma'am.
Okay, now let us see what is brute force based concept learning. How we go forward with a crude method, and then later how we refine the concept learning, base concept learning. Okay, brute force is just going blindly with whatever we come across. We can design a straightforward concept learning algorithm to output the maximum a posteriori hypothesis. You know what is maximum a posteriori hypothesis, right? You calculate the posterior probabilities of various hypotheses, and whichever hypothesis has the maximum probability, that is called your maximum a posteriori hypothesis. This I explained in your first lecture. You remember? HMAP. This is called as maximum a posteriori hypothesis. You calculate the probabilities of all the best solutions and take out the one with high probability, that is called your maximum a posteriori hypothesis. And this is based on Bayes' theorem as follows. Let me explain. Brute force map learning algorithm. How it looks like? Initially, what is the first step? For each hypothesis H, in the hypothesis space, capital H, calculate the posterior probability. You doesn't know which is the maximum a posteriori hypothesis, means you doesn't know which is the best one among all the solutions. So what you're doing, calculating their likelihood, calculating their probabilities. Now, whichever hypothesis has higher probability, that is your maximum a posteriori hypothesis. Okay, so calculate first all the hypothesis probabilities. Probability of H given D is, according to Bayes' theorem, probability of D given H multiplied by prior probability of H divided by prior probability of the training examples D. Okay, now in the second step, output the hypothesis H map with the highest probability. How do you denote that? H map is equal to argmax for all the hypotheses in the hypothesis space H. Wherever the probability of H given D is maximum, that will be your H map. Very straightforward, right? Once you understood yesterday's example, how you derived this formula of H map, it is easy for you to understand this brute force map learning algorithm. Just two steps. Calculate posterior probability of all the hypotheses, means what you're doing here, you're trying to find out the likelihood of all the hypotheses and select the hypothesis with maximum likelihood, with maximum chances of becoming true with the given training examples. Okay, that is the output hypothesis H map with the highest probability, highest posterior probability, that is represented as argmax of among all the hypothesis H belonging to the hypothesis space capital H, select the probability that is maximum, posterior probability that is maximum. That is nothing but your H map. Hypothesis, maximum a posteriori hypothesis. Is it easy to understand now? Now let us choose probability of H, probability of a hypothesis becoming true, and probability of hypothesis becoming true means what would be the hypothesis? Say in the context of bank, bank giving loans. For that particular bank, 95% of the people who took loan have cleared the loans. That is called as prior probability of hypothesis. A statement is made, and what is the probability of that statement? 95% of the customers paid back the loans. So the probability of H is 0.95 here, clearing the loans. The fact is about clearing the loans. That is 0.95. and probability of D given H. Now, you observed some new examples. Now, what is the probability of that examples are in compliance with your statement made? Whether this new set of people are clearing the loan or not clearing the loan, into which category they fall. That probability is given by probability of D given H. Now let us choose these two probabilities to be consistent with the following assumptions. Remember, whenever you are making a machine learn, you have to make some assumptions. If you do not make any assumptions, in that case, your finalizing of your hypothesis will become complex task. As I said, if you in decision tree algorithm we have considered, right, only conjunctions. We haven't considered disjunctions, because if you start considering disjunctions, your tree will grow complex and complex. That is why you are considering only conjunctions, and your assumption there is you have to consider only shortest trees which are simple, and you have to consider a statistical measure called as information gain in order to select the best decision tree. That is the best hypothesis for your training examples given. Like that, you have to make some assumptions in order to arrive at a generalizable hypothesis. If you doesn't make assumptions, your learning task will become complex and your machine learning model will be less generalizable. It will cover all possible say combinations of the attributes. In that case, it can't generalize well to the new data. That is why assumptions are very important in concept learning. So what are the assumptions that are made here? The training data D is noise free. We are assuming that at present the training data is noise free. It doesn't have any outliers. It doesn't have any missing values. It doesn't have any duplicate values. Okay, we are just assuming it is noise free. That is, the training example directly helps us to calculate the learn the concept, helps the machine to learn the concept. That is the target variable, yes or no, defaulter or not, loyal customer or not, genuine transaction or not. That is the concept. And to learn this concept, the training examples are directly enough. You don't have any error E associated with it. Okay, that is given in simple terms as the training data D is noise free. It doesn't have any noise. It doesn't have any deviations that will lead to wrong predictions. Now, the target concept C is contained in the hypothesis space H. That is our second assumption. We can't say that, we can't be pessimistic. Whenever you are making a machine to learn, you should start with some optimistic approach. That is, the target concept C is contained in the hypothesis space H. We are assuming that. Now, we have no a priori reason to believe that any hypothesis is more probable than any other. Say in your hypothesis space H1, H2, H3, you have three hypotheses in your hypothesis space H. Now, you don't have any knowledge about which hypothesis is more likely, which hypothesis is having higher probability. You have to train the model. You have to make the machine learn from the training examples given and calculate the probabilities for all these hypotheses and find out the hypothesis which has the maximum probability of being consistent with the training examples. That will be your maximum a posteriori hypothesis. That will be your best hypothesis that explains the behavior of your training examples. Did you understand? Now, given these assumptions, what value should we specify for P of H? Let's see. Given no prior knowledge that one hypothesis is more likely than another, we don't have any knowledge, we don't have any prior knowledge, prior probability knowledge is nil here for us. It is reasonable to assign the same prior probability. This I have been repeating again and again. When there is no knowledge about prior probability, you have to assign same prior probability to every hypothesis H in the hypothesis space H. Simple, right? You have prior probability knowledge, you keep it. You give, say in our previous example, 8 out of 1000 population have cancer. That is prior probability. We have some knowledge about the general population, but in some cases we may not have that prior knowledge. In that case, you have to assign equal probability to all the hypotheses in the hypothesis space. You have 3 probabilities. The probability of each hypothesis is 1 by 3. You have 10 probabilities in the hypothesis space. The probability you assign to each hypothesis is 1 by 10. Okay. Now, furthermore, because we assume the target concept is contained in H, we already assumed this, that we have the solution in hypothesis space H. We should require that these prior probabilities sum up to 1. All those probabilities should sum up to 1. Because if one occurring, the other doesn't occur, right? So the probability of any hypothesis of any event occurring is 1. But you don't have knowledge whether that event will occur or not. That is why you are giving equal probability 1 by n to each of those n hypotheses in the hypothesis space capital H. Now together, these constraints imply that we should choose. How do you choose the probability of a hypothesis? The probability of each hypothesis? 1 by number of hypotheses in the hypothesis space. Say if you have n hypotheses in the hypothesis space, then it is 1 by n. That we are generalizing. We are writing a general mathematical notation here. That is 1 by number of hypotheses in the hypothesis space H. That probability you assign to each of the hypotheses H, small h. To each of the hypotheses small h, what is the probability you assign? If there are n hypotheses, it is 1 by n. That is represented by absolute value of H, means number of hypotheses in capital H, hypothesis space H. Okay, that I am representing. If there are n hypotheses, then it is 1 by n. Now the probability of data D given hypothesis H is 1 if D is consistent with H. We know that, right? If the probability of the data D for a given hypothesis being in compliance with the statement already made is 1 if they are consistent. Okay, this data is applying for this statement made, means D is consistent with the hypothesis H. In that case, we write it as 1. Probability of D given H is 1 if DI is equal to the hypothesis. That is, the training example is in compliance with the hypothesis, is in accordance with the hypothesis. Then it is 1 for all the training examples in D. If D is not consistent with the hypothesis, means this training examples are not in accordance with the statement made. They are contrary. They are opposite to the statement made. Statement is made according to one set of training examples, but a new set of training examples you have gathered. This statement is not applying. You are finding some new trends in this data. 95% of the customers are paying back the loan, but you have gathered another sample in which most of the customers are not paying the loan. Then how can you say 95% of the customers are paying back the loan? Right? Means you're saying that probability of these observed training examples in consistency with the statement made is lower. They are not in consistency with the hypothesis made. In that case, you give it as 0. Data is in accordance with the statement made, it is 1. Probability of D given H is 1. Data is not in accordance with the statement made, probability of D given H will be 0. Understood? Let us consider the first step of this algorithm, which uses Bayes' theorem to compute the posterior probability P of H given D of each hypothesis H given the observed training data D. Let us consider that formula. Let's recall that Bayes theorem. It is probability of H given D. How is it calculated? Probability of D given H multiplied by prior probability of H divided by prior probability of D. Now, the posterior probability of hypothesis inconsistent with D is what? 0, right? H is not suiting D. The observed training examples D are not in accordance with the statement made. Means the posterior probability of D given H will be 0. Now, consider the case where H is consistent with D. Yes, H, the hypothesis made, is consistent with D. The training examples observed D is consistent with H. In that case, we write probability of D given H in the Bayes theorem, the first term, it is 1, right? Because they are consistent with each other. So it is 1. Now, what is the prior probability of H? You have no idea about the prior probability of H. So you assign equal probability to all the hypotheses in the hypothesis space. That is represented by 1 by mod, absolute value of H. Means the number of hypotheses in the hypothesis space H. Okay, did you understand? Probability of D given H when D is consistent with H is 1. That you have substituted. Now probability of H, you don't have prior probability knowledge, so you are assigning equal probability to all. That is 1 by mod H. That also you are substituting here, divided by probability of D. Write it as it is. Now let us further refine our knowledge what we have about these measures that are given. Now numerator, keep it as 1 into 1 by absolute value of H. That is number of hypotheses in the hypothesis space H divided by, now what is this probability of D? Probability of observing these training examples irrespective of any hypothesis. You just have the knowledge about the hypothesis space, that's all. But which hypothesis suits for this training example, you doesn't know. In that case, we can write it as number of hypotheses in the version space which are consistent with D. You want to count now. Divided by the number of hypotheses in the hypothesis space H. That will give you the probability of D, prior probability of D. Okay, so that you are substituting here. Now removing this denominator, you have the final posterior probability as 1 by the number of hypotheses in the version space which are consistent with the training examples D. That is our final posterior probability P of H given D. Very clear, right? Did you understand now how we arrived at this? What is posterior probability of H given D? We want all the probabilities where H is in compliance with the training examples D, but we want the maximum out of them. That is H map. But if you want to consider only the posterior probabilities, how many of them are actually existing? That is nothing but 1 by divided by what are the number of hypotheses in the version space that are consistent with the training examples. 1 by version space HD. If you want probability of H with no prior knowledge, you write it as 1 by number of hypotheses in the hypothesis space H. Now, how do you calculate the probability of H, posterior probability of H given D? It is nothing but 1 by the number of hypotheses in the version space which are consistent with the training examples, right? That will give you the posterior probability of H given D. Very simple to understand. If you understand each and every step, what values are substituting the previous values, it is very easy to derive the final result. And that is quite obvious, right? Whenever you want to calculate the posterior probability of the hypothesis, it is nothing but the probability of the number of the probability divided between the number of hypotheses in the version space that are consistent with D. That is why you have represented it with V as H of D. Number of hypotheses in H that are consistent with the training examples D. Is it very clear now? Any of you want me to repeat this again? This derivation? It is straightforward. There is nothing hidden in this. You are just substituting what prior knowledge you have. Probability of H shares equal probability because you don't have any prior probability knowledge. That is why you have substituted with 1 by mod H. Now, probability of D can be calculated as version space of H given D divided by number of hypotheses in the hypothesis space. How we are calculating probability of D is, probability of D is observing the training examples irrespective of the statement made. So that, but you want to find out all the hypotheses that are consistent with these training examples. That is why you are considering the version space HD divided by the number of hypotheses in the hypothesis space. Okay, now to summarize this brute force based concept learning, Bayes' theorem implies that the posterior probability P of H given D under our assumed P of H and P of D given H is, how do you write it now? Now you have derived a simpler version which is easy to see and understand. Before, maybe if you say H consistent with D, it is little complex, but here see, probability of H given D can be represented as the shared probability of all the hypotheses in the version space that are consistent with the training examples D. I'm saying shared probability. Shared probability means if there are n hypotheses, the probability will be 1 by n shared between all those hypotheses. Okay, that is why I'm saying shared probability. So this probability of posterior probability of H given D is nothing but 1 by the number of hypotheses in the version space that are consistent with D. Here D is given. That is why you want all the hypotheses that are consistent with D only and 0 otherwise. Means if they are not consistent with D, then the probability of that hypothesis is 0 because it is not consistent with the training examples given. And hypothesis space doesn't contain that kind of hypotheses which are not consistent with the training examples. That is why its probability of being in the hypothesis space will become entirely 0. Its likelihood of being in the hypothesis space will become entirely 0. Why? Because it is not consistent with the training examples given. Now, evaluation of probabilities associated with hypothesis. Understand this carefully. Very simple concept, but if you don't pay attention, you will not understand this at all. Very simple concept. Just focus. Initially, all hypotheses have the same probability, right? Initially, when you don't have knowledge about prior probability of something, you have to share the probability 1 among all the hypotheses, right? For that, see this figure. Initially, the probability of the hypothesis, it is linear. All are sharing equal hypothesis. You understood this? Now, as training data accumulates, see figures B and C. As training data accumulates, the posterior probability for inconsistent hypothesis becomes zero, right? Among these hypotheses, say there are 10 hypotheses here, H1, H2, H3, H4, all these hypotheses initially they are having equal probability. Now, you started observing training examples, which will give you more and more knowledge about these statements made. Initially, you say 50% of the Indian population are recovering from COVID. 50%. You made some hypothesis. Yes. Now you started gathering more and more data about the patients recovering. As you see more and more data about patients recovering, your hypothesis your likelihood will increase. Likelihood of the patients recovering will increase. Means it will become 60%, it will become 70%. Now you observed some 10 million Indian population, Indian patients data, and among them 90% recovered. In that case, your hypothesis will start becoming narrower and narrower and grows with respect to one particular hypothesis. Initially, here 4 hypotheses are sharing equal probability. But see, when training example 1 observed, there is more knowledge about the probability of this hypothesis. So it becomes narrow, and with respect to one hypothesis, it starts increasing. And with respect to other hypothesis, it starts decreasing. It says that H1, H3, H4 are not consistent with the training example D1. So their probability reduced and H2 probability increased. Why? Because it is inconsistent with the training example that is observed. So that probability increased. Did you understand now? So say H1, H2 are here. Their probability reduced because D1 is not giving any proof in support of H1 and H2, and neither it is giving any support to H4 also, but it is giving support to H3. Means the probability of observing H3 when the data D1 is given, when the training example D1 is given, is more now. Okay, now another training example is observed, D2. In addition to D1, D2 is also observed. Now, say initially this is H4 also is applying for this. Now, H1, H2 and H4 are not showing any compliance with the hypothesis. Only H3 is consistent with the training example D2. That is why its probability increased. On the y-axis you have probability. Did you observe? Probability of the hypothesis H becoming true with respect to the training examples given. Now, after observing D2, initially when D1 is observed, H1, H2 are having very less probability because they are not consistent with D1. But it is observed that H3 and H4 are consistent with D1. So, its probability increased a little. Now, another training example is given, D2. Now, after observing this, it is observed that even H4 is not consistent with D2, but H3 is consistent with D1 as well as D2. Now this probability of H3 increased little more. Now you keep observing the training examples, 100, 1000, million training examples. Now, after observing these million training examples, which hypothesis holds good for all these million training examples? That will be your most probable hypothesis. That posterior probability of that hypothesis given the training examples, given million training examples, will be the highest. That is your maximum a posteriori hypothesis. So every consistent hypothesis is therefore a maximum a posteriori hypothesis. Say you have 2 hypotheses that are consistent with the training examples and both are having equal probability. In that case, you can take both of them as maximum a posteriori hypothesis. But most of the time, you will get one hypothesis which is having maximum likelihood to be observed for the given training, for the given training examples. Okay, this is how you need to understand map hypothesis. Now, what is the relation map hypothesis and consistent learners? Every hypothesis consistent with D is a map hypothesis. That we understood, because every hypothesis is applying, is in compliance, is in accordance with the training examples that is observed. Means this statement made is always being supported by the training examples given. Now, when it is being supported, that statement will be your declarative statement. You declare that these many customers are paying back the loan. And that will be your map hypothesis. That will be your maximum a posteriori hypothesis. Now, we'll say that a learning algorithm is a consistent learner provided it outputs a hypothesis that commits zero errors over the training examples. That is our ultimate goal. Any learning algorithm is a consistent learner. How it becomes a consistent learner? When it makes zero errors in the prediction. When it makes zero errors in its generalization. In that case, we say that the learning algorithm is a consistent learner. Now, given the above analysis, we can conclude that every consistent learner outputs a map hypothesis, right? When you have taken a learner, say neural network learner, or a decision tree learner, or finders learner, or candidate elimination algorithm you have used for the learner. In that cases, if it identifies the maximum a posteriori hypothesis, then we say that learner is consistent learner. Given the above analysis, we can conclude that every consistent learner outputs a map hypothesis if we assume a uniform prior probability distribution over H. What is uniform prior probability distribution? Every hypothesis has same probability. That is P of Hi equal to P of Hj for all Ij in H. And if we assume deterministic noise-free training data, what is deterministic noise-free training data? It is not random. The data is not random. It is deterministic. It is static. And we assume this deterministic and noise-free training data, that is P of D given H equal to 1. You have some data that is consistent with the hypothesis. And if it is not consistent with the hypothesis, we assume that as 0. Assuming these, assuming that the data is deterministic, assuming that the data is noise-free, and assuming that all the hypotheses in the hypothesis space share equal probability, in that case, if a hypothesis is consistent with the training examples, then the probability is 1. Otherwise, it is 0. In that case, you can find out the maximum a posteriori hypothesis by applying this algorithm. Now in the next class, that is after 10 minutes, we'll start maximum likelihood and least square error hypothesis. This is easy concept to understand, do not worry. Okay, so take 10 to 15 minutes break because I want you to be fresh to understand the next concept again very clearly. So take 10 to 15 minutes break and come back. We'll start the next concept. Now before leaving, can you just tell me what is Bayes' theorem? I purposefully repeated the terms again and again so that you will not forget it at all. What is Bayes' theorem? P of H given D can be calculated as? Quickly, students. What is P of H given D?
P of D given H
P
into
of D
D
given H.
into P of H
Good. By
divided by P of D.
P of D. Very good. This is Bayes' theorem. Posterior probability. Read this. Please read this as posterior probability of H given the training examples D. It can be calculated as posterior probability of D being observed in a world where hypothesis H is true, multiplied by probability of H, prior probability of H, divided by prior probability of D. Okay. Now what is map?
Maximum posterior.
Maximum a posteriori. You're hungry, you're swallowing the last part. Tell me
No,
completely. Maximum?
a posteriori.
Maximum. A posteriori hypothesis. Okay, I should have written it as map hypothesis, right? Maximum a posteriori hypothesis. That is the hypothesis that is having the high posterior probability. What is ML? We have written as HML, right? What is HML? Maximum likelihood, that we are going to learn in the next class. ML is the maximum likelihood of this hypothesis being observed in consistence with the training examples. Okay, yeah, take a 10 minutes break and come back. We'll start.